So welcome to lecture 11 of the solar photovoltaics course. So we will just first do a bit of recap of last lecture. So in the last lecture we started talking about, we talked about the band diagram of a semiconductor of P and N type semiconductors. We looked at the variation, so we looked at how Fermi level are aligned in P and N type semiconductors, how do they vary as a function of dopant concentration, and so we saw that in a P type semiconductor the Fermi level is closer to the valence band edge, below the intrinsic Fermi level, and in the N type semiconductor Fermi level is above the Fermi level of intrinsic semiconductor, that is slightly above the closer to the conduction band edge, and as it gets closer to conduction band edge upon doping or valence band edge upon doping, it tends to become like a metal. So when the difference between the Fermi level of P or N type and the conduction or valence band edge, valence or conduction band edge becomes less than 3 kT, then the semiconductor becomes a degenerate semiconductor. It becomes like a metal, it starts behaving like a metal. And then we also looked at Fermi energy versus composition, or let us say doping, and then we started a bit of discussion on conduction in semiconductors. So in conduction in semiconductor, the conductivity of a semiconductor is given as so sigma n plus sigma p. So it is for both N and P type carriers. So sigma n would be due to electrons, which is because of Ne, you can say Q mu E, and this would be NH Q into mu H. So this would be the overall conductivity. So we'll take this discussion forward in this lecture, and what we also did was we did a bit of discussion on what are the different types of currents that you can have. So you can have current due to drift and diffusion. Okay, so we will again revisit some of these topics and further discuss these. So as we saw that drift current is equal to J, so you can say Jn is equal to Ne Q mu E into E, because J we know is equal to sigma E according to Ohm's law. Okay, so this is drift electron current, and the drift peak hole current is NH Q into mu P or mu H into E. So you can write it as mu P or mu H, these terms sometimes get interchanged. Okay, so this is basically hole mobility. And we also looked at in the last classes the variation of mobility with respect to doping and variation of mobility with respect to temperature. So as you dope it further, the mobility keeps dropping, and as you increase the temperature, again because of phonon scattering, the mobility drops. So J drift current, total drift current is, so J drift total will be equal to Jn drift plus Jp drift. So this is drift. So this will be equal to Ne Q mu E E plus NH Q mu P mu H into E. So that will be the total drift current that we will have for a semiconductor. So based on this, we can define now the resistivity . So resistivity basically, so we write for conductivity, we write J is equal to sigma E. So this is in terms of conductivity. Okay, and in terms of resistivity we write E is equal to rho J. So which means sigma is equal to 1 over rho. So basically resistivity is reciprocal of electrical conductivity. So you can say that if J was equal to Ne mu E Q E plus NH mu H Q E, if we take it out, then this becomes Ne mu E plus NH mu H into Q into E. So this is a term which is sigma. So reciprocal of this will be the resistivity. So resistivity is 1 over Q into mu E Ne plus mu H NH, or Ne mu E plus NH mu H. So this is the electrical resistivity of semiconductors. Now you can obviously see from this, if you have for n type semiconductor, you know that Ne is equal to Nd, which is a lot greater than NH, okay, right. So as a result, the resistivity of a n type material will be equal to 1 over Q, you can say Nd into mu E for a n type, right. Similarly, for a p type semiconductor, since NH is equal to Na, which is a lot greater than Ne, you can define rho as 1 over Q Na into mu H. This is for p type semiconductor. Now the way, I mean, of course, so resistivity measurement in this case measurement of resistivity is basically done using what we call as 4 probe method. So essentially 4 probe method is the one which because metal and semiconductor often have contact resistance, and for measurement of conductivity you would require metal contacts to be deposited. So to discount the effect of contact resistance in calculation of resistivity, generally we use this 4 probe method instead of 2 probe method, which is generally used for metals. So what we have here is we have so if this is your wafer, then on the surface of wafer you make 4 contacts, equally spaced contacts. So what we have here is, so we have 4 probes here. So this is the first probe, this is the second probe, okay, and from these you flow the current in, okay. So this is for I. So current is flown in this fashion, and these are the other 2 probes which are connected to a voltage measuring device. So you measure the voltage across these. So the spacing between these is S, let's say, okay. So you are using 2 probes for flowing the current in, and outer 2 probes for current to flow, and the inner 2 probes to measure the voltage. This prevents you to the contact resistance which is between the tip and the semiconductor, because you will have to deposit a metal contact pad at this point, and often there is a contact resistance. To discount the contribution of voltage drop at that contact resistance, you use this 4 probe method. So essentially the resistivity is computed as rho is equal to 2 pi s V divided by I into a factor f, okay. I can write it differently. This is the factor F, and this factor F is basically calculated by doing the by the plotting. So you can say that S is here probe to probe spacing, and F is you can say a tabulated or graphed correction factor. So if you do the measurements at various voltages and currents, you can get this, and this depends upon sample thickness, and whether the bottom of semiconducting. So this is semiconductor. Here this is the metal contact, and this is the probe, metal probe. Okay, so it's so it depends upon whether how is the bottom. So whether this so on what surface is the semiconductor kept, basically that is what. So it's a easy method, generally very useful method for measuring the 4 probe resistance, and the measurement of mobility is done through Hall measurement. Okay. Hall measurement, which is basically you have a current carrying conductor and you apply the magnetic field. So you basically measure the Hall voltage, or so basically based on Hall effect. Capital A, Hall effect, and this will tell you whether one, it tells you whether semiconductor is P or N type. So by the sign of the Hall voltage you can find out whether it's a P or N type semiconductor, and secondly one can determine the mobility, carrier mobility can be determined. So Hall effects, you can find any book on Hall effect, and this can do these measurements. Now then next we move to in semiconductors. Before we go to diffusion, you need to know about the energy, a few things about energy band diagram. So in semiconductors, so semiconductors band diagram, and there are some terminologies that you have to know. So for example, if you have a semiconductor band diagram like this is your EC, this is your EV, conduction band edge and the valence band edge, and this is basically the distance x. Okay. So as you go away up from EV to EC, the electron energy is basically increasing. So this is total electron energy increasing, all right. And if you have the representation of carriers is basically, generally electron is depicted as a dot and a filled circle, and hole is depicted as a empty circle, and the carrier motion is opposite. So if if hole moves this way, electrons move this way, the motion is opposite, and hole energy will decrease in this fashion. So this is hole energy, sorry, increasing, this is hole energy increasing. Okay, this is increase in hole energy. And if you have a carrier, So if I draw another picture here, so if you have a carrier, for example, little bit above the valence band, then this much amount of energy which is available to the electron is basically the kinetic energy of electron. And if you have a hole sitting somewhere here, then with respect to EV, this much energy is the kinetic energy of hole. So if you want to now measure, for example, with respect to electron, so this is the energy level at which electron is, and let us say you have certain reference energy level, okay, E ref. Then the potential energy of electron will be equal to, so this is the total energy, right, of electron, out of which this is the potential energy contribution and this is the kinetic energy contribution for electron. Another thing which is important in semiconductors is the band bending. Okay, band bending generally happens because if you have differences, for example, in electric field, or if you have differences in any other thing. So essentially, let's say you have a so band bending can be represented by something like this. For example, if your semiconductor is non-uniformly doped, if it is non-uniformly doped, which means its Fermi level will be different at different places. If its Fermi level is different at different places, which means since Fermi level is different at different places, but chemically the thermodynamically material has to stay in equilibrium, which means your material will have, so you can have a situation like this in which Fermi level is equilibrated like this. So this is the EF equilibrium. Okay, I have written it other way around. So, but you can see that in this side you have valence band being closer to Fermi level. In this side you have conduction band being now to equate the Fermi level on the two sides, because you have two compositions on two sides, there has to be a band bending. So this is where you see that there is a what we call as band bending at the interface, and this is because of differences in composition of two sides. Fermi level is different on one side, Fermi level is another on other side, but since they are connected to each other, chemically electrochemically speaking, material has to be at equilibrium thermodynamically. So to ensure that material is at thermodynamic equilibrium, the Fermi level is at the same level throughout the material, but what it requires is that shifting of the conduction and valence band will be shifted in different parts of material in such a manner so that you have band bending at the interface. So this is the region at which, so this is, you can say, in this region you can say it's P type, in this region you can say this is N type. So if you have these composition differences, you can have another picture like this. Let's say you have a semiconductor, piece of semiconductor, in which the composition varies like this, okay, as a function of distance. Let's say this is Nd as a function of x. All right. If you want to plot for this, how will you plot for this? So what this will have is, since this is varying, Nd is varying, but material will remain in thermodynamic equilibrium, which means Fermi level will stay here. On this side the Nd is higher, on this side the Nd is lower, all right, which means the valence band will be farther on this side, conduction band will be farther on this side and closer on this side. So this would be your energy band diagram, sort of. It is exaggerated, but this is the way you will have band bending taking place in the material. Of course, it's, I don't know if it's N or P. I mean, here it looks like as if you have gone from very N type to very P type, but this is how it will probably vary in a material. Okay, it may not be to this extent. If it's purely N type, the slope may be something like this. Let's say the slope may be something like that. Okay. So you can see again you have a band bending. Band bending means you have some electric field here. So basically you have an electric field here in this region. Okay, I will come to that. So essentially in such a situation, if you have band bending, then if you have a reference energy level is this E ref, then your potential energy is changing as a function of distance. The potential energy is something here and potential energy is something here, right. So so you can say that PE in this case is equal to EC minus E ref, alright. Now if potential energy is changing, what it means is that, so if I now draw the similar picture in such a fashion, and if I say PE is equal to EC minus E ref, now if I want to draw, this is the E ref and this is what is PE is measured as. Okay. If I now want to determine what is the potential V as a function of distance x, the potential goes as, according to laws of electrostatistics, minus 1 over q into EC minus E ref. Okay. This is the definition of potential on the relating the electron energy with the voltage or potential. So this goes as, because potential is nothing but E divided by Q, but Q is negative, it goes as negative of energy. So this goes as, basically you can see, since this goes in this fashion, the potential will go in other fashion. So it will go something like this fashion. Okay. Now let us plot the electric field. This will be useful when you learn the PN junction. Electric field is minus of del V, right. So electric field by definition is minus of del V. If you now plot the electric field, this is so in this part it is 0, in this part it is 0. So it is 0 here, it is 0 here, but it goes as something like this in this region, like somewhere here you will have change of slope, right. So this is how electric field will plot itself. Now if you want to plot another thing which is called as charge density, now we are plotting charge density which is proportional to dE over dx. So if you now want to plot charge density, and if you again take this as a, so this will be essentially something like that, the charge density. Essentially you can see the negative charge density is equal to positive charge density within the band bending region. So essentially electric field is symmetric here. So total amount of negative charge is equal to total amount. Solid has to be at the end electrically neutral, which means total of positive and total negative charge should balance each other. So that is what will happen here. Now let us move to, so this is an important exercise, how to draw the energy band diagram, and from the energy band diagram how to determine the potential, how to determine the electric field, how to determine the charge density. Sorry, this should be rho. Okay, and remember potential energy is with respect to a reference, and for electron it goes increasing in the up direction, and for the hole it goes up in increases in the other direction. Potential is minus of let us say delta E divided by Q, or minus of E divided by Q. Electric field is you have to watch out between the E for energy and E for electric field. So maybe you can write this as in this fashion. So the electric field is nothing but minus of del of V by definition, and then charge density is proportional to electric field gradient dE by dx. So these are the 4 definitions that you have to remember, and this tells you how to draw the potential versus distance, energy electric field versus distance, and charge density versus distance for a semiconductor in its band. Now let us move to the next topic called as carrier diffusion. So what we will do is that we will do the carrier diffusion in the next class. So let me just summarize what we have done in this class. So in this class essentially we have looked at carrier drift and resistivity, which is inversely proportional to the conductivity. Then we looked at resistivity measurements, which is made by 4 probe method. Then we briefly talked about mobility measurement, which is done using Hall measurement. And then we looked at the energy band diagrams, band bending, plotting of potential, electric field, and charge density. So these are important exercises you will have to do at some other systems, considering other situations at home. I would recommend you to go through this book by Robert Pierre, Semiconductor Fundamentals. Volume 1, and Advanced Semiconductor Fundamentals, Volume 6. You can also go through SMZ, Physics of Semiconductor Devices. This is again a very good book to give you idea about the semiconductors. So these are few books which may be useful for you to improve upon your understanding of semiconductors in general, especially these 2 volumes by Pierre, Semiconductor Fundamentals Volume 1 and Advanced Semiconductor Fundamentals Volume 6. These are really good books for improving your understanding of semiconductors. Okay. So we will stop here. We will do the next lecture in which we learn about the diffusion. Thank you.